So, my name is Charlotte Wolf, and my exploration is mathematical models and epidemiology. So, epidemiology is the study of the incidence, distribution, and possible control of diseases and other factors relating to health. Using mathematical models, the risk of death from specific diseases can be understood, as well as making attempts to limit the infection with vaccination or quarantine. Mathematical modeling also allows for the analysis of patterns in statistics and the prevention of outbreaks without human testing. This topic has been brought to light for much of the world in 2020 with the outbreak of the coronavirus in China, which further piqued my interest in this topic. So, SIR models are a visual representation of the statistics of specific diseases. They assist in understanding what steps need to be taken to help control the outbreak of the disease and later prevent it, as well as just a visual way of looking at the spread of a disease in terms of the population percentage. So, S in SIR stands for susceptible, which is individuals that are susceptible to the disease. I stands for infected, which is individuals that are infected and who are able to transmit the disease to others. And R stands for recovered, which is individuals that have recovered or are immune to or have died from the disease and don't contribute to the transmission of the disease. So this is an example of an SIR model. We can see the S is in blue here, and it represents the susceptible people, the number of susceptible people. I is in red down at the bottom, and it represents the number of infected people who are able to transmit the disease to others. And R is in green, and it stands for the number of recovered people. And the x-axis we have days, and the y-axis we have percentage of the population. So there's many variables that go into an SIR model. So V is the recovery rate of the infection. D is the duration of the infection. Beta is the contact rate, which is how likely someone will get the disease when in contact with someone who is ill. R of O is how many people an infectious person will pass their infection to in a totally susceptible population. V of T is the amount of population needed to be vaccinated. And then D of T is time. So then D of S, D of I, and D of R are, or DS, DI, DR, are the number of susceptible people, the number of infected people, and the number of recovered people. And then S of T, I of T, I of T, and R of T are the same thing, just another way to write it. So I'll get to this later, but V and beta are the two things that you actually put into the SIR modeling technology, but the other variables contribute to and help solve for those two values. And then the two values that you don't solve for but that I've researched for are D, the duration of the infection, and R of O, which is how many people an infectious person will pass their infection to. There are also a number of different equations used to determine each variable, like I said. So with D, which I researched, you can use it to find V. With R of O, which I also researched, you can use it to find beta, also using V. The value that you got from the equation above, and then V of T you can solve for using R of O, which I researched. And then these last two equations, I'll go more in depth with this, but they're too complicated to solve by hand, so I used modeling technology. So after researching the components of an SIR model, I did further research to find diseases that have been relevant and that are interesting in the past 20 years. So I ended up choosing 3 diseases: tuberculosis, influenza, and coronavirus, to kind of make my exploration more interesting, and also, like I said, just because the diseases are relevant and connect to the real world more than like a disease that occurred 100 years ago. So now I'm going to go through each of those 3 hand-solved equations and why they make sense and what variables they're related to. So D represents the duration of the infection, and V represents the recovery rate, so it makes sense that the duration of the infection would be equal to 1 divided by the recovery rate. Or, another way to solve for it is V equals 1 over D. This also makes sense because the recovery rate is a value that is less than 1, so to obtain the value for the recovery rate, 1 is divided by the duration of the infection. So then, for V of O, So V of O represents the percentage of the population needed to be vaccinated in order to contain the disease. So therefore, it makes sense that the value would be calculated by dividing 1 by the average number of people that a single person may pass the infection to, which, like I said, is R of O, which I researched, and then subtracting that value from 1. This creates a value that's less than 0, and it's interpreted as a percentage because it represents the ideal vaccination goal for a population in order to contain the disease. So then last, for the equations, we have R of O. So in this equation, we're not solving for R of O because, like I said, I researched for it. So R of O is the number of people that a single person may pass the infection to, and beta, which is what we're solving for in this equation, is the likelihood of someone getting the disease who's in contact with an infected person. So it makes sense that R of O and beta are related. They're also related to V, which represents the recovery rate of the infection. Because all these variables are related to the spread of the disease, it can be understood why they are all related and in the same equation. So the first disease that I modeled was tuberculosis, which became relevant again in the United States in 2007. The values that are bolded below are values that I researched and didn't solve for myself. So the duration of the infection for tuberculosis is 14 days approximately, and the number of people that an infected person can pass the infection to is 10. And I used those 3 equations to solve for V, which I got. The divide sign didn't show up here, that's a typo, but it should be 1 divided by 14, or 0.07. And then when I solved for V of t, it was 90%, and beta is 0.7. So then here are the calculus equations, which again, I'm not sure what Google Slides did, but it deleted a lot of the divide signs, so it should be ds divided by dt, di divided by dt, and dr divided by dt. Yeah, so d is, so here's all the equations that I used to solve for those values that I just said in tuberculosis. So for D, using D, which is 14, I got V, which is 1 over 14, and, used R of O to get V of t, which is 90%, and then I used R of O to get NV to get beta, which is 0.7. So the last 3 equations are, like I said, these are the calculus equations, so they're too difficult to solve by hand, but there's a computer program that plots the graph based on the values entered for S, I, and R. I would link the program, but it doesn't exist anymore, unfortunately. I'm glad it wasn't deleted before I could finish my exploration, but it's gone now. So my first model for tuberculosis was created based on the population and SIR values displayed below. So my hypothetical population, for each of the hypothetical populations for all of the models I made, I got them off of the IB Math Resources website because it said that was the best way to model a disease in terms of 3 models over time. So the first model for every disease has the same hypothetical population as well as the second and the third. So the total people in this population is 10 susceptible, 1 infected, and 0 recovered with a time length of 30 days. And the 2 values that I entered are beta, which is 0.7, and V, which is 0.07. So from this model, we can see the progress of each of the values. For S, the number of susceptible people immediately experiences a sharp drop. The number of infected people rises at a sharp rate, then falls at a steady rate. And then the number of recovered people rises at a steady rate throughout the 30 days. So for model number 2, like I said, the population for model number 2 and all the diseases is the same. There's 1,000 people, with 1,000 people susceptible, 1 infected, 0 recovered, and the time length is 30 days. So Beta again is 0.7, and V is 0.07. Beta and V stay the same for all three models of a disease, but it's the population that changes, so you can see how it would change in a different population, in different populations. So model number 2, the number of susceptible people plateaus before dropping sharply. The number of infected people briefly rises at a sharp rate and then falls at a steady rate, and the number of recovered people rises at a steady rate and then plateaus. So model number 3 for tuberculosis, the hypothetical population is 1,000 total, but only 100 susceptible, 1 infected, and 900 recovered with a time length of 30 days. So this model is the most different from the other ones, and I'll explain why on the next slide. But everything's at a plateau. And it's different because I didn't put herd immunity into this because I was going to explain it. I forgot to delete that part. But there's 900 recovered people out of the 1,000 people in the total population. And 900, yeah, okay. So those who are susceptible are protected from the infection, and because no one is recovering from the disease, the number of recovered people in the population, which is 900, remains constant. So, like I said, herd immunity is the resistance to the spread of a contagious disease within a population, and it results from a sufficiently high proportion of individuals that are immune to the disease, especially through vaccination. So because there's 900 recovered people out of the 1,000 people in the total population, those who are susceptible are protected. So the second disease that I modeled was influenza, and I'm going to be going quicker through these next diseases because I already went through all the models of tuberculosis, so I'm just going to go through these ones more quickly. So influenza, duration is 4 days, and the number of people you can pass the infection to is 2. And here are all the other values that I solved for. Here's the equation process. And so the first model is based on this population and time length. Same for tuberculosis, the first model. And beta is 1 and V is 0.25. So, yeah, from the first model, number of susceptible people drops and plateaus. The number of infected people rises and then falls and then plateaus. And the number of recovered people rises at a steady rate and then plateaus. Model 2 for influenza. Hypothetical population is the same for the second model of the other diseases. 1,000 total, 1,000 susceptible, 1 infected, and 0 recovered. Time length 30 days. And beta and V are the same for all of them. And number of susceptible people plateaus and drops, and then plateaus again. The number of infected people rises and falls, and the number of recovered people steadily rises before plateauing. Then model number 3, hypothetical population, is the same for all of the number 3 models, and beta and V are the same. So it's the same case with all of the model number 3s, because of herd immunity, like I explained, and those who are susceptible are protected from the infection. So the third and final disease that I modeled was coronavirus, which first became relevant in the United States in January of 2020. But before I reveal the variables, I'm going to let you guys solve for 3 variables yourself. The variables that you're going to solve for are highlighted and listed below, each with their respective equation. So I'm going to go to the next slide for more information before solving. So here's the first variable that you're going to solve for. In order to solve for V, the variable D needs to be known, and for coronavirus, D equals 5.2. Pause the video, substitute this value into the equation below, and solve for V. When you've gotten your answer, unpause the video for further instructions. So I'll give you a couple seconds to pause it and then move on. Okay, so next we're going to solve for beta. So in order to solve for beta, the variable R of O needs to be known. For coronavirus, R of O equals 2.5. You'll also be using the answer that you got for variable V in the last equation. So pause the video, substitute V and R of O into the equation below, and solve for beta. When you've gotten your answer, unpause the video for further instruction. Okay, so then our third equation and last equation that you're going to solve for with is solving for V of t. So for V of t, the variable R of O needs to be known. And like I said, R of O for coronavirus is 2.5. So pause the video, substitute this value into the equation below, and solve for V of t. When you've gotten your answer, unpause the video for further instruction. Okay, so here are the answers. Here's what your work and answers should look like for the three variables you just solved for. For V, you should have gotten 1 over 5.2. For V of t, you should have gotten 0.6 or 60%, which again, it's a percentage because V of t is the number of people needed to be vaccinated to contain the outbreak. And for beta, you should have gotten 0.48. Okay, so here are my models for coronavirus. I solved for beta and V. So for beta, I got 0.48, and V simplified was 0.19, and here's the population and time length. So the number of susceptible people slowly drops and then plateaus. The number of infected people briefly rises and then falls. And the number of recovered people rises at a steady rate and then plateaus. The second model was created based upon the same population as all the other number 2 models, and the same beta and V values. So the number of susceptible people plateaus before experiencing a slow drop. The number of infected people plateaus before slowly rising and then slowly dropping, and the number of recovered people rises at a slow rate. The third SIR model was created based upon, again, same population for the number 3 models for all the diseases and same beta and V values. So the model number 3, like I said, for all of them looks the same because of herd immunity. Like I said, I already explained this. So what I learned from this, let me just pull up my notes here. Okay, so this exploration ultimately taught me about how diseases are modeled and how vaccination numbers are determined in terms of population numbers. The main section of my exploration was mathematical models, which I successfully created with the help of software that was provided on the IB Math Resources website. And the process of creating these models was also successful using the equations that I outlined above. So weaknesses with this, it was the accuracy of the values I got from the equation. So it was hard to find accurate values for each of the variables. Like I said, I researched for the duration of the infection and the number of people that somebody can pass the infection to. And I found the diseases on the CDC website, which is the Centers for Disease Control and Prevention, but it didn't provide the values that I needed, so I had to do the research and use a different website for each disease that I modeled. So the results of the equations aren't completely accurate. It was difficult to find just a really reliable constant value. Another measure that I could have taken to test the accuracy of modeling the diseases with SIR models was to find a disease that had already been modeled with an SIR model along with each equation and value used to create the model, and then recreated it with the same steps that I used with the models in my exploration. Yeah, so basically the biggest thing was just the accuracy of the values that I got. It was hard to find a reliable value, but I did the best I could with that. So my overall thoughts. I love this exploration. I've always been interested in epidemiology and human conditions in general. it really taught me a lot about how diseases are modeled and studied, and it was just really interesting, which is why some assignments and projects are just hard to accomplish because there's something that you're not interested in and it just takes a long time. But this really didn't seem that hard to me because I love doing it and learning about it. Especially because my favorite class last year was forensic science. And when I saw this on the list of exploration ideas, I knew it was perfect for me. The fact that infectious diseases specifically affect most people also intrigues me, and I wanted to explore how dangerous diseases are observed and modeled in order to prevent them and determine data such as how much a population needs to be quarantined or how many vaccines need to be administered to a population. I also love how this became, well, it was already relevant when I started, coronavirus hadn't happened when I started doing this exploration, and then I was originally only going to do tuberculosis and influenza, but then coronavirus happened, and I thought this would be the perfect opportunity, so I chose coronavirus as one of the diseases that I modeled, and it's been really cool to see that be relevant to my life now, because obviously we're all in quarantine. So, yeah, this was my math presentation, and I hope you like it.